Let's talk about redox reactions in electrolytic cells. This is a part 3 video of our electrochemistry playlist. Electrolytic cells involves electrolysis. Let's define electrolysis. The chemical process in which electrical energy is converted to chemical energy, or the use of electricity to produce chemical change, is called electrolysis. This basically means that we can use a battery to bring about a chemical change or to drive a chemical reaction. In electrolytic cells, we'll do things a little bit different compared to galvanic cells. The electrons will still flow from the negative terminals to the positive terminals, but in this case, the positive terminal will be called the anode, and the cathode will become a negative electrode. These polarities are vice versa compared to the galvanic cells, which we discussed in part 2. However, this is to maintain our definitions of an ox and a red cat. So at the anode, oxidation still happens. At the cathode, reduction still happens. Usually in the electrolytic cells, we'll use electrode which won't react with the electrolyte like PT or graphite. Once again, the electrolyte is the solution which contains anions and cations. The electrodes used in electrochemical cells will carry electrical current in and out of the electrolyte. The positive electrode, which is defined as the anode in electrolytic cells, will attract the negative ions, or what we call the anions, in the electrolyte. As we see in the sketch, so here's our negative ions being attracted to the positive electrode. And if our electrolyte, for example, is copper chloride, we will have the chloride ion attracted to the positive electrode, the anode, because they are negatively charged. The electrons that will be found on the cathode will then reduce the cations. So the negative electrode, which is the cathode, will attract the positive ions, as we see in the sketch. So in this case, the copper 2 plus ions will then be attracted to gain 2 electrons and become copper solid. Net ionic equation looks like this, and the E naught cell calculated will become a negative 1,02 volts. This tells us that the reaction is non-spontaneous. Then if you look back on the sketch, let's look at what happens in the reaction. We can see bubbles forming on the positive terminal, which attracts the negative ions, which is this equation here. Then you can notice that there is a gas forming, which is our chlorine gas. When this happens, the electrons on the chloride ion will then be lost. On the cathode electrode, we can see a copper metal deposit because copper 2 plus from the solution is gaining 2 electrons to become copper solid. This particular electrolytic cell is called the decomposition of copper chloride, which also means the breaking down of copper chloride into chlorine gas and copper solid. Let's look at more applications of electrolysis. First, we'll look at electroplating. Electroplating is a process whereby a metal object is coated with another metal to improve its appearance or to protect it. For example, let's look at the electroplating of a nickel spoon with a silver coating. Here is the process of electroplating. The object to be coated is placed at the cathode. The anode is metal X, the one you want to coat by. The electrolyte in solution should contain metal X ions. So the focus will only be on metal X, in this case silver metal. So we can see the electrolyte in solution is silver nitrate, which matches the silver metal which we want to coat with. Notice that the positive terminal of the battery is connected to the metal we want to coat with, and that's silver. So we can say an ox happens at that electrode and a red cat happens on the spoon. The silver is undergoing oxidation, or it's losing electrons, and it's on the anode side. And red cat means that reduction is taking place at the cathode, which is a negative terminal in electrolytic cells. Let's observe what happens when the cell is allowed to run. So we can see that the silver electrode is losing mass while the nickel metal is being coated with a silver deposit. Let's look at the half cells to see what happens. At the cathode side, we have silver Ag plus aqueous gaining an electron to become Ag solid. This is why there's a deposit, because a reduction is happening on the cathode side. At the anode, we can see a silver is losing its mass because it is becoming Ag plus, which drops into solution, thereby releasing one electron. So what we see here is that the same metal is oxidized and the same metal is reduced. Let's now look at purification or the refining of metals, which is another application of electrolysis. Impure metals such as impure copper can be purified by the process of electrolysis, which we call electrorefining. In this process, stronger oxidizing agent impurities will not be oxidized easily, so they will sink to the bottom. We call this sludge. Let's look at this example in particular. We know this is an electrolytic cell because we see a battery connected. We can see a pure copper electrode which is connected to the negative terminal of the battery, and we call that a cathode. The impure copper, the one to be purified, is connected to the positive end of the battery and it's called an anode. We can see some impurities that are inside the impure copper, which may be dirt or some other metals. For the purification to be possible, once again the electrolyte has to contain copper ions. In this case, we'll use copper sulfate in the electrolyte. So we know the positive terminal is the anode where oxidation happens, and the negative terminal is the cathode where reduction happens. So on the anode side, where we have the impure copper, we are going to have copper being oxidized or losing electrons and then falling into solution as copper 2 plus. While on the cathode side, we see the copper 2 plus being picked up onto the copper electrode. We call this reduction. So here we can see that the cathode will contain the pure metal X, in this case copper, and the anode will contain the impure metal X, which contains the metal we want to collect on the cathode. Once again, the electrolyte has to contain metal X ions, in this case copper 2 plus ions. Take a look at the diagram to see an animation of what happens when we let the cell run. So we can see the impurities dropping down and the pure copper being deposited on the cathode copper. Then we call this sludge once again. And now all the pure copper that was contained on the impure copper is now deposited on the cathode copper. We can then write the half reactions. We see at the cathode there's the reduction of copper. So copper 2 plus ions are gaining 2 electrons to become copper solid. That's why we see a gain in mass. That's why we see a gain in mass on the cathode side. At the anode, we see the copper that has impurities becoming copper 2 plus and losing 2 electrons. What we realize in both electroplating and purification is that the concentration of the electrolyte remains constant. Why does this happen? Pause the video and think about it. Here's the answer. So looking back on the electroplating side, we can see that when the Ag metal is dropping inside the solution to become Ag plus, it's making the Ag inside the solution to be more concentrated, while at the same time, the cathode side is picking up 1 Ag from solution. And these reactions will happen simultaneously, which means 1 Ag is going into solution and 1 Ag is being picked up from the solution. So this maintains the concentration of the overall electrolyte. Same thing happens on the purification side. When the pure copper from the impure sample becomes copper 2 plus, another copper 2 plus from solution is being picked up to the cathode to become copper solid. So when copper is being gained in the electrolyte, copper is being lost from the electrolyte. so the overall concentration of the electrolyte stays the same. Now we'll look at an example. This one was taken from question 9.4 of the November 2021 final exam. The question says the diagram below shows a simplified electrolytic cell used to electroplate a ring. Calculate the total charge transferred when the mass of pure chromium changes by 2 grams. So due to the presence of a power source, we know that we are dealing with an electrolytic cell. We are told that the chromium metal will lose 2 grams. Because this is electroplating, which immediately tells us that chromium solid is going to be dropped into solution to become chromium 3 plus ions. We know that the ring will have to pick up chromium 3 plus ions to be reduced to chromium solid, so that it can have a thin coating of the chromium metal. Let's now look at an animation of what happens when we let the cell run. So we can clearly see the mass loss of the chromium electrode, and we can see the coat of chromium on the ring. Therefore, the half reactions will look like this. At the ring, chromium 3 plus aqueous is gaining 3 electrons to become chromium solid. And at the chromium metal, we see that chromium solid is becoming chromium 3 plus aqueous and therefore losing 3 electrons. Then we see that red cat is happening at the ring, and we have an ox at the chromium electrode. So this is what you do whenever you are presented with a question. You analyze it, you break it down, you get all the half reactions, you do everything to break down the question and interpret it before even checking the questions. So this is what we have now. Let's look at the solution. Step 1. We calculate the number of moles of chromium from the mass that is given. So the mass of chromium given is 2 divided by the molar mass of chromium, which is 52 grams per mole. So we get 0.038 mole. Remember, we are looking for the total charge transferred, and we know that charge is carried by electrons. So we are going to analyze electrons. In other words, if we find the number of electrons being transferred, we can then determine how much charge is being transferred as well. So to find how many electrons are transferred, first we need their number of moles, which brings us to step 2. We already know the number of moles of chromium, so we can use this equation to find the number of moles of electrons. So we can say that we compare chromium with electrons. The balancing coefficient is 1:3. In other words, for 1 chromium which is oxidized, we release 3 electrons. We know the number of moles of chromium is 0.038, so we can find the number of moles of electrons denoted by N into E minus. Then we cross multiply, we see 1 multiplies N and 3 multiplies 0.038. So we can say the number of electrons in this reaction is 0.115 mole. Knowing the number of moles of electrons, we can go to step 3, which involves this equation, which says N, which is the number of moles of electrons in this case, is equal to the number of electrons, which is denoted by big letter N, divided by Na, which is the number of molecules inside 1 mole. And we call that Avogadro's number in chemistry application. So we can rewrite the equation this way to find the number of electrons transferred. Substituting, we get 0.115, which is the number of moles of electrons, multiplied by the Avogadro's number. Then we get 6.95 times 10 to the power 22 electrons, which are transferred. Then step 4, we use the equation that will give us how much charge we get from how many electrons we have, which says number of electrons equal to the charge over E, which is the charge of an electron. So once again, this equation says that number of electrons, this is not moles in this case, and this one says the charge, while E, sometimes they use QE, means that the charge on an electron, which is a constant. You should be familiar with this equation since grade 10. It is also given in the paper 1 formula sheet, but not in paper 2, unfortunately. You just have to remember it in case there's a question like this. We can rearrange the equation in this form to find our charge. Then we substitute the number of electrons, and then we substitute the constant, which is the charge on one electron, which is a value of 1,6 times 10 to the power negative 19 coulombs. And then we get the charge which is being transferred in this reaction is 11,113,85 coulombs. And that question is done. If you have further questions on this example, please address them in the comments. And if you want to join my live online classes, go to the description to learn how to do so. In the next video, we will talk about the industrial electrolysis process, which is the chloralkali industry. Cheers.